So today what we're going to be looking at are titrations, an introduction to titrations. Now titrations are a very common technique used in chemistry to work out the strength of acids and alkalis. And this is an introduction, so this is just going to tell us about the bits of equipment that are used, how to prepare them, how to read numbers off of the bits of equipment, and how you would know if an acid was stronger or weaker than another acid using a titration. So with this, we should probably show you what a titration experiment looks like. And what we have here is we've got a picture of a titration experiment. A titration experiment looks like this. So obviously we've got a clamp here, and we've got a flask here. Now the flask, usually we'd call it a conical flask, just because of the shape of it. And in here, you would put, depending on the circumstance, you'd put your acid or your alkali. In this case, we'll put our alkali in here. And you need to know the volume. Of that. And you put something called an indicator in. Now, universal indicator is a type of indicator, but we don't tend to use indicators like universal indicator in titrations. I'll come back to talking about indicators later on. But the most important bit of equipment for this experiment is this thing, and it's called a burette. So a burette is a bit like a measuring cylinder. It's got all these marks down the side of it which tell the volume, but it's got a tap at the bottom. And what's also a bit strange is that the numbers start at 0 at the top and they go down, depending on the size of the burette, it could go down to 10, could go down to 25, could go down to 50 centimeters cubed. Now the reason for that is because in a measuring cylinder, you fill it up this way and you empty it that way. So you empty it through the top. But a burette is designed to fill it up to the maximum here, and then you empty it from the bottom into the flask. And so as it empties, you can read off 1, 2, 3, 4, etc. how much you've added. So this is used for adding liquid when you don't know how much you're going to add, but you want to measure it very accurately. And that's what the burette is known for. It is very accurate. It's, in fact, one of the most accurate bits of equipment that you ever get to use in a chemistry lab. And you use it whenever you do not know the volume that you're going to add. Now I'll get an even closer look at the burette here. So we've got a tap that controls the flow. Now in this position you can see that the tap is sort of running this direction. And if the tap is like that, that means it's open. If the tap is sort of running that way, where it's flat, then it's closed. So you want the bar, you sort of turn it that way, and that stops it from going. And depending on how much you turn it, you can turn it a little bit. You can either make it have a constant stream of liquid coming out the bottom, or you can have just a drop coming out at a time. That's what makes it so accurate, is that you can use it to add a lot of liquid at once, or you can add just one drop at a time. And it's got very accurate numbers. Now when it comes to reading a burette, seeing how much liquid is inside it, it's a bit complicated. Not really complicated, because you're used to seeing this with measuring cylinders. But what happens is that when you put liquid in it, the liquid doesn't have a straight line. It doesn't do like this. It ends up curved. And so if this was filled, you'd see a curve like that. when you're wanting to read it, I'll go with zoomed in version here. When you're wanting to read it, you need to read it at eye level. So when you're reading it at eye level, what you can either do is move it up and down on the clamp so that it moves to your eye level, or you can lower your head down so that you are looking at it at eye level. Now this curved part here, that bit I've just drawn over, that's called the meniscus. I've spelt that wrong, meniscus. And again, I might have spelled that wrong, might be with an I, apologise, but it's the meniscus. And it's always curved like that for water. Different liquids, it can look different, but for water, it always curves downward. And what you're looking for is where the bottom of that line is. And you can see here that this measures, a burette measures to 0.1 of a centimetre cubed or a milliliter. And you're expected to be able to read off that value to 0.1, or if it's between two lines, you can estimate it to 2 decimal places. So if it's halfway between 20 exactly and 20.1, you can say it's 20.05. But you're always looking for that, and you have to make sure that you're looking at eye level. So when we have the experiment set up like this, we have our alkali in here, and we fill this with acid. And that's what we do. We add the acid to here. That's the basis of the experiment. Now we'll get into more details. But first, we'll look at how do you prepare the burette. We'll move that to the side. So preparing a burette. There are several stages. Stage 1 is you clean it with deionized water. What deionized water means is that the water is very pure. It means it doesn't even have small ions inside it. So that's very pure water. But it's important that we talk about it being deionized water. The second thing we do is we then rinse it with the acid. We rinse it with the acid, and typically we have a funnel on top to help us do that. And we make sure that the top of the burette is below eye level. So sometimes what you'll need to do with the burette is move it up and down so that you can safely use the top, and then raise it back up so that you can look and see at eye level where it is. But when you're filling the burette, you want the top of the burette at eye level or below so that you can see what you're doing. Now we've rinsed it with acid. That's just a rinse through and let it go the whole way through. Then we need to fill it with acid. And again, we need to use a funnel, and we need to make sure it's below eye level when we're filling it. And you can fill it slightly above the zero. Fill it slightly above zero, and then use the tap to have the meniscus. on 0. And 0 exactly, so sitting on the line. And you can, every single time, you can reset it to 0. You can top it up with more liquid. Now once it's filled, you need to check that there are no air bubbles. And that the tap is closed. Now this seems like a lot, but actually this process doesn't take very long to do. You clean it through with deionized water, you rinse it with acid, and you make sure that you're using a funnel, because the opening at the top of a burette is quite narrow. And if you use a funnel, it just makes it safer. You then fill it with the acid, and you make sure that you get it just above 0. Use the tap to have it so that the bottom of the meniscus is on 0. And you want to make sure that there are no air bubbles, especially at the bottom, and that the tap is closed. And then before you want to use it, you just need to take the funnel out before using it. So you do that, you take the funnel out before you use it, and then it's good to start. And what you do next is you need to prepare your flask, the conical flask, the thing that sits at the bottom. So you're preparing this bit here. And this one we're going to use the alkali. Now what we need is we need to use a pipette. So a pipette is a bit of glassware designed to hold exactly one specific volume. So they come in all different sizes. They could be 5 centimeters cubed or 5 mils, 10 milliliters, 25 milliliters, 50 milliliters. You use a pipette. And this needs rinsed with water. Again, it has to be that deionized water, and then rinse with your alkali. Then you fill with alkali, and then transfer it, put into your flask. That's a bit easier. So you put it into your flask, and then you're done. You filled your burette. You filled your burette with acid, and you have put your alkali in a beaker. Now we're going to look at this thing here, the indicator. So, an indicator the type of indicator that we use for a titration typically has a colour change. So it's in acid, it's one colour, and in alkali, it's another colour. So there are lots of different indicators. So some indicators are red, so it could be red to blue. That's litmus. And then there is one which actually is pink and colourless. And I always forget which way around it goes. But I think it is pink in acid and colourless in red. But it doesn't matter. It's obviously a distinct colour change. And the point where the colour change happens so it either goes from red to blue, pink to colourless, could be orange to pink, red to yellow, depends on the indicator, we call that the end point. And the end point, that means that neutralization is complete. You've added enough acid to your alkali to fully neutralize it. And so that's what you're doing. An indicator is just something that changes between two colours, and the point at which it changes is our end point that tells us that neutralization has happened. Okay? So now we've got our flask and we've got our burette. Already, we've got our flask, we've got our burette. To do the experiment, we do what we call a rough titration first. Now, a rough titration, that just means we open the tap and, not being very cautious, we just let the acid flow into the alkali. We hold the flask and we sort of stir it a little bit to let them mix better. And we watch where the colour change. So once the colour change happens, we close the tap. Close the tap immediately. So once you see this flask change colour, we close that tap immediately, and then we read how much acid. So read the volume of acid. Now that's a rough titration. Burettes are designed for accuracy. So then what we do is see how much was added. So say, for example, if this was 18 centimetres cubed. Well, then what we do is an accurate one. An accurate reading. And this time we set the burette up again, and this time, say if it was 15, we open the tap, and once it gets to about 16, we do that fast, then we slowly add our acid. We try and do it what we call dropwise, so one drop at a time. And we can do that by turning the tap so it's almost closed and only a little bit of liquid can get through. And once we add the drop, each drop, give it a stir. Once the colour change happens, close the tap, and we might see that it's less than 18. Usually it is. So this time we might have got 17.6 centimetres cubed. Now even that is not good enough, believe it or not. When you're doing a titration, you have to keep doing your titrations until they are 0.2 centimeters cubed apart, maximum. And when we do that, that's what we say our results are concordant. Are concordant, that just means that they are 0.2 centimeters cubed apart. Once you've got two results that are concordant with one another, you take the average. The best case scenario is that rather than being concordant, they're exactly the same, and then you don't need to take an average. but concordant is that. So say you did one titration, you do your rough titration, your first, your second, your third, you might sometimes need to do a fourth one. And in each titration, you read off, well, what was the starting volume? So with your rough one, you call it the initial reading, then the final reading. That's just the volume on the burette. You don't always have to start at 0. And then what was the titer? And that just means the volume. So the rough one maybe started at 0.0, got to 18.0. And that means that the titration was 18.0. This one we always ignore. So the rough one, we always ignore. We only ever look at the results after the rough one. So say the next one, they put it back to 0.0 and they saw that it was 17.6. So that means they've got 17.6. Okay, next time, they didn't quite fill it up to 0, they started it at 5.0 and they got to 22.3. So that's 17.3. Those two results are not concordant because they are 0.03, they're 0.3 apart. Okay, so next one, did it again to 50. And this, sorry, to 5. And 5, they got to 21.9. 21.9. And that was 16.9. Still not concordant. So they need to do it again. This time, they only filled it to 10. And they got to 26.8. This number, take away that. That means that the volume was 16.8. So the way that I'm working this one out, this is your final minus your initial. So this number, subtract this number, gives us this. So these two are concordant. So we take an average. Average of two numbers, add them together, divide them by 2, and that gives us 16.85 centimetres cubed for this one. 16.85 centimetres cubed is our average titer. Now, why would we do that? Well, later on we'll see that we can do it to work out concentrations, but we're not going to look at calculations involving that. What it can be used for is to compare how strong or how weak an acid or alkali is. And so we do a set of experiments. So we have 3 acid samples. Let's call them A, B, and C. And we don't know which one's the strongest, which one's the weakest. So what we do is we do a titration of all these 3 different acids. We titrate them against one molar, so 1 mole per litre. So that's an exact concentration of sodium hydroxide, which is an alkali. So that means the sodium hydroxide was in the beaker. Sodium hydroxide was in the beaker, and we filled our acid one at a time. We start with A, then we do B, then we do C, and we do a titration. Now we find out, after we do the titration, we get to concordance, we find out that A used 10.1 centimeters cubed to reach the end of the reaction. B, well, it needed 25.3 centimeters cubed, and then C, well, C used 8.7 centimeters cubed. And we look at those values and we want to work out which acid must be the strongest one. And when we have a situation like that, the least amount of liquid, or least volume, that we need in order to fully neutralize that must mean that that acid is the strongest one. So with the titration, more concentrated, or we can say stronger, means lower volume. The more concentrated, higher the concentration of the acid, the less is needed to get to the end point. So in this case, if we wanted to go from strongest to weakest, we compare these numbers. Now the one that had the lowest volume was C, so that's going to be our strongest one. The one that had the biggest volume of this list is B, so that's going to be our weakest one. And A is in the middle, so A goes that. So C, A, B. So that's how titrations are done and how they are used to compare acids against one another. Now this topic we'll come back to after you've looked at some calculations, but this is an introduction. I know this lesson has a lot of information in it. So we'll just go over the equipment. The name of the special bit of equipment is a burette, and it is very accurate. What's very special about it is that it's got a tap at the bottom. Now if the tap goes up and down, it's open. If it goes across, it's closed. The numbers start at 0 and go down, usually to 50, but it can be smaller than that. And as it goes down, you can read what volume you have added. Now whenever you're reading it, you need to be at eye level, and you're looking for the bottom of that curve. That curve is called the meniscus. The bottom of that curve tells you your volume. And a burette allows you to read the volume to 1 or 2 decimal places. So it's very accurate, a lot more accurate than a measuring cylinder. Now, whenever you are preparing a burette, you need to make sure that firstly, you clean it with water, then you clean it with your acid, and then you fill it with acid. And you might be using a funnel to do that for safety. Once it's filled, you make sure that the bottom of the meniscus is at 0. Then you take your funnel out and you're good to go. For the flask, the bit at the bottom, here, you're using a thing called a pipette to fill it, which again, you need to rinse with water, then rinse with your alkali, and you fill it with your alkali. And there's a line on it that tells you when you're done. When you're doing a titration, you always do a titration once, which is the rough one, to give you an idea of how much acid you're going to need. Then you do accurate readings, and you keep doing accurate readings, accurate titrations, until you get 2 volumes, at least 2, that are 0.2 centimeters cubed apart. And that is what we call your results being concordant. Once you've got concordant results, you take the average. So in our example that we did, first one, we always ignore it, it's rough. And then we can see we kept doing titrations until we got results that were within that 0.2. These results are concordant, and then we take the average. And our average, we work out to 2 decimal places. In order to see the end point of the reaction, we need to make sure that we put an indicator in our solution. And an indicator is just a chemical that is one colour in an acid and a different colour in alkali. And the point where the colour change happens, we call the end point of the reaction, and it means that neutralisation has happened. And we can compare the endpoints for different acids to see which one is most concentrated. The more concentrated an acid is, the less volume is needed in order to reach the endpoint. So the more concentrated, the stronger the acid, or the more concentrated the solution, it means lowest volume. So in a set of results like this, if we wanted to work out which one the strongest one was, we look for the one with the lowest volume. So that has been an introduction to titrations. I know it's a lot of information, but it is a good place to start. So again, as always, thank you for your attention.